So, okay, so our next speaker is Anuradha Annaswamy from MIT, and she will talk about the connections between adaptive control and learning. Thank you.
Thank you. Thank you, Bartholomew, for the invitation. It's a pleasure to be here with you all. Almost everybody I met here, except for Melanie and Sarah, I think, are new, so it's nice to make new friends and spread the gospel of adaptive control. So this is an area that I've been working on for the past several years, and I still feel after, I don't want to say how many years, I still feel like I've only scratched the surface. And as this workshop is really exploring the intersections between optimization, control, and learning, adaptive control really fits like a glove, especially in the connection between control and learning. And I'm really glad Melanie went before me and set the stage for all of the important aspects of what control addresses. And so this makes it really easy for me to launch into what my topic. Again, like all of us, our students and former postdocs and so on are the ones who do the work, and it's a pleasure for me to present their work with you. This work is sponsored by Boeing and Air Force Research Lab, among others. And let's get into it. So this is sort of roughly the outline that I'm going to walk you through. So let's start with the idea that we have in a complex dynamic system and control goals. And again, as Melanie and Francesco yesterday talked to you about what the ingredients are, we are trying to understand, we're trying to actually shape the response of a safety critical system so that whatever the system goals are met. And the problem is that we have to figure out how to massage the exogenous variables that are indeed under our control. And how do you do that in real time so that you really are able to accommodate uncertainties and constraints that might be present in the problem. And there are various ways in which you do that, and there's a lot of hierarchical structure, like Melanie just was talking about at for the last question. So there are things that you plan ahead of time, and there are things that you need to tweak in a faster time scale, and that's where the outer loop and inner loop and everything comes into the picture. We want to make sure, first and foremost, when you do all of those things, that everything stays stable. You are robust to whatever you did not really put into the design model, and that's the next aspect that you worry about. You worry about safety. You don't want to definitely wander into regions that really can be deleterious. And of course, you want to do all of these things so that you save money, you save time, you save energy, you preserve the quality that you're looking for, and so on. So how do you do all of these things even while you accommodate uncertainties is really sort of the narrative that I'd like to walk you through, and at the same time meet constraints. So this is a long story, and it's been going on even before I was born, even though I was there when dinosaurs used to roam, I think. So it really comes from water clocks and fly ball governors, and you can go all the way to BC, but the story is actually something that really gathered steam around World War II, and there's a whole lot of applications where closed loop control has really met its mark, and there's a whole bunch of success stories that have been recorded in various reports over the years, and of course now we understand some of the ideas of this nexus between the physical world and the cyber world, and there are again various sectors that have benefited with in terms of figuring out what the right marriage is, and the story is only getting more ambitious as we go along. We really want to address how some of these approaches can be developed, not to just solve engineering problems, but really societal scale challenges. And I'd like to direct you to this roadmap that tells you more about what exactly are the different glide paths that we need to tackle in here. So in all of these things, what's the role of adaptive control? And so the idea here is very much an emphasis on real time. And you have your physical layers, and you've got your uncertainties in whatever you're trying to control. But there are also other things that you cannot anticipate, that you cannot put in your distribution, you cannot put in your training set. And those things could be simply various kinds of anomalies that occur that you cannot anticipate beforehand. And you want to make sure that you are indeed able to figure it out on the fly. That's sort of the emphasis in here. So that's a slight different shift in the focus of what we're trying to do and the kinds of uncertainties that are expected to occur in the problem. So the idea of adaptive control basically is then to say, okay, I'm going to assume that the structure of the problem is such that I have an idea of where the underlying model comes from, but what I don't have are an understanding of what the parameters are for various reasons. It might be that I designed the system, in which case I knew what all the physical constants were, whereas over time, there were anomalies that I didn't anticipate, and therefore there are some uncertainties. And so in this particular case, and again, you've seen this a few times before, and so you've got your dynamics, and it's your parameter that you do not know. And the distinction here is that variables are indeed quantities that vary with time temporally, much faster, whereas parameters are relatively slowly varying. And that's sort of the distinction that we make in here. So then, what the adaptive controller does is really to figure out a way in which you can do a real-time correction, and the control basically adjusts itself, and it's in the form of adjusting perhaps the control parameters so that your control input indeed does the right thing. And typically what you have are, these are the kinds of structures that the approach that you use, where you both have a control input and a specific way in which you adapt the parameter. And I'll come back, keep circling back to this, what we call as the adaptive law, and talk to you about what exactly is the role that it plays and what's the nexus between adaptation, control, and learning. So the way in which adaptive control sort of approaches this whole thing, and there's a sort of a philosophical point in here, and that is that there are two kinds of errors. And this is something that pervades all of problems where you're dealing with uncertainties and you really look at the concept, the word adaptation, as a, where it really comes from biology, that we're trying to figure out what to adjust so that we kind of make sure that some performance goals are met. So there are two kinds of errors in here. There's a performance error and there's a parameter error. And one is something that I can measure. That's the one that gives you this loss function idea. And the other are the weights, the parameters that you can actually adjust. And these could be PID control gains as well. And so the learning rule tells you how exactly you should adjust it in real time based on the performance error that you can measure. So the question is, what's the right performance error? What's the right loss function? What's the exact parameter that you need to adjust? And there's so many of these questions have been answered over the years. The reason why it's really difficult is because these two errors don't always nicely correlate, the parameter error and the performance error. And so the goal, the way in which adaptive control really has progressed is to figure out what this error model is, the relation between these two errors. Then that sort of gives you a handle on the problem. So how do you do that in different contexts is the question. So let me try to sort of explain it to you in the context of a very simple linear regression problem. This is something that, again, we've seen, perhaps not so much in this workshop, but those of you who have looked at various problems in optimization, learning, and control, and machine learning really have this linear network quite a bit and is ubiquitous. So you have something called a regressor, and the regressor, a linear combination of the regressor is what you are interested in, and figuring out what it is. And so you build an estimator, and you look at the corresponding performance error. And here in this particular case, theta is the unknown parameter, and then you have to figure out a way of estimating it, and that gives you the parameter error. In this particular case, if you choose the E squared as your loss function, there's actually a very nice convex relationship that you can get, and that gives you a great handle on the problem. And so you use this gradient descent, which again, you've heard many of the speakers talk in this workshop, and everything is great. But the problem is that, and this is what we call as our model 1 in the adaptive parlance, but the problem is basically that this doesn't always work. And this doesn't work because often there is a lag between the parameter error that you really want to get rid of and the performance error that you're measuring, especially when you have complex dynamic systems. And because of this lag, it turns out that if you could measure this E prime, which actually has a convex relationship to the parameter error, it's great. But unfortunately, that's a signal that you don't have, and it's internal to the system. And so you only have E, which is a quantity with a certain lag, and that lag can actually kill you. And that basically is what people realized, and you can see, we are talking about 1966, and that's kind of when the foundation for adaptive control really got laid. So this is the reason why we pivoted and really went towards a stability framework. And so the idea is, don't look for a gradient descent and try and make that work, because you can't, and look for something like a Lyapunov function and see if you can find a positive definite function which you can make into a non-increasing one and make it into your Lyapunov function. And the way you can do that is, even though the quantity, the adaptive rule that you're looking for is not something that is like a gradient descent algorithm, it still works because you basically have a particular candidate that you can make into a Lyapunov function. So this is the idea, and this sets the foundation. And if you look at going back to the error model 1 that I talked to you about, then you think that this is the kind of nice shape, but it doesn't always look like this, and therefore you need to pivot and really look at a stability framework, and that's the one that gives you the answer. In this simple example, the two coincide, but in general, it isn't, and that's the reason why you need to really develop different learning rules when you're dealing with complex dynamic systems. And this is what we have done over the years. And so, for instance, here is a problem when you have several states that are accessible, and I'll loop back again to this towards the end of the talk, but talking about adaptive LQR, which has been looked at quite a bit in recent literature. And so the idea here then is there is this target, and that target comes from what we call as a reference model, and that in turn gives you this error, the performance error E, and that's what you're after, and that gives you then a way in which you can figure out what the adjustment rules should be, and bingo, there is a nice Lyapunov function that gives you what you want to do. And you can extend the story to a problem where you have only partial observations, so then you need to interlace an observer that basically gets combined with a controller, and then there is a notion of a separation principle, which you can't quite really employ in here because you have a nonlinear problem in the sense that your parameter estimation depends on the control input, and the control input is affected by the parameter estimates. And that introduces nonlinearity, and this is known as a dual control problem, and you really need to break that loop. And the structure that I'm showing you on the screen here is one that does that. And it basically says that you have to have a search in a higher dimensional manifold in order to really make sure that you can design the controller and have it give you stability before you go to learning of the parameters. So that's a very important separation that really led to, again, solidifying the foundation for adaptive control. And that also, again, gives you global stability, and there are tools that we can use in order to show that this performance error actually goes to 0. And we can extend the story for nonlinear control as well. And so, again, coming back to many of the kinds of problem statements that Melanie was showing you, here you are looking at a nonlinear system, and there are many problems where you can introduce some structure into it, like using the regressor phi of x, and that allows you to again, provide some simplifications in terms of what the structure of the adaptive nonlinear control should be. And it turns out that you can indeed find suitable functions that tell you how to adjust the parameters. And of course, all of this is predicated on knowing something about the structure of the problem. And if you know that this is a blended wing body, you know that it's a combustion system, or you know that it's an autonomous vehicle with say, for instance, you're trying to do fuel-air ratio control, whatever the underlying problem might be, since you know something about the underlying physics, you utilize all of that to say, okay, I have some structure that is known, and I'll leverage that structure in order to design the controller. So this is, okay. Let me see, maybe this itself will do it. So this is an experimental result that we have in our lab. And what you see in here is a problem where there was a real-time uncertainty that was introduced because a part of the propeller blade broke midstream in flight. And what you saw, the first run there is a non-adaptive solution, which obviously did not really rise to the occasion, whereas the adaptive controller figures out that you need to adjust the control gains in real time and was able to do that and therefore have the stable hover and recover the performance. And so it says then that all of these tools that we showed were practically validated in that context, and there are many other such examples. And so on top of all of these parametric uncertainties, what if you had other unstructured uncertainties, other modeling errors and time delays and so on? And so what this says is that you would then take that adaptive controller, integrate it with a baseline, and you can still provide robustness guarantees to unknown actuator dynamics, whether it could be due to time delay or because of unmodeled dynamics. And both of those things basically are addressed by either having a regularization type of thing, which is, again, a tool that is known to many of you, or projection. And it, again, depends on how severe the constraints, the anomalies are, whether you make it a hard constraint and therefore use a projection or do something soft, which gives you the regularization type of idea. And there are also things called dead zone, which says don't adapt when you think that this might be due to some non-structured uncertainty. So I would like to shift the story to constraints, which is, again, something that we've been hearing about quite a bit in many of the talks. And so there are two kinds of constraints that we can accommodate into this adaptive control structure. One of them is magnitude constraints. So you see the notion, again, I want to go back to the performance error and the parameter error story. You need to know what you're adapting to. And if you think that there is a certain kind of uncertainty, and that's really the one that's your story thread, then that tells you that this is your performance error. But if what you're looking at is due to a varied set of mechanisms, and not necessarily because you have parametric uncertainty, then you're adapting to the wrong thing. And that can lead you to trouble, big trouble. And so you need to therefore figure out as to what the structure of the problem is, and when are you hitting the limit of your actuator, and when are you really suffering because of the effects of a modeling error, of a parameter uncertainty. And so to be able to distinguish between the two, what we did was just to really model the effect of saturation as an additive disturbance, and that allowed us to modify the performance error, and therefore that very simple change basically did the job. And the nice thing about this algorithm is something that it has met up with a lot of success in a variety of applications, and over the years we have collaborated with a number of different researchers. So here is one example, for instance, in propulsion systems. In fact, I added that slide, Paul, just link with the conversation that we had yesterday. So it's a collaboration that we had with Anne Dowling at the University of Cambridge. And it's a very interesting combustion system dynamics, where this essentially resonance produced because of an intrinsic feedback between heat and pressure. And it basically sets up a resonance in a closed chamber. And that is coming because of the specific kind of geometry that you have and the specific kind of operating conditions. And what we were able to show was that by using adaptive control, which comes in cold and knows nothing about what the system dynamics is and is able to have a significant reduction, and these are actual experimental results from a scaled Rolls-Royce rig that shows that compared to the baseline, and you can see that this is something that you can actually hear depending upon the kind of frequency. It's either a buzz or a hum or a screech. And what we were able to do was by pulsing the fuel using feedback measurements from various pressure sensors along the length of the chamber, we were able to kill the resonance. And here is another one, which is a simulation result for a hypersonic vehicle, where the assumption was that, again, midstream in the flight, you are introducing parametric uncertainties. And the story here is that you have to do all of these things in terms of adaptation, even while keeping the input saturation, both in terms of magnitude and rate, to be within the limits. And what you're seeing at the top are basically the control input rate, and this is the corresponding control input. And what you see is that if you're not really able to honor the limits, then this is something that is not really desirable. Whereas if you meet the elevator rate limit, you can still meet your performance, and the adaptation basically is able to figure out, as you can see in the red dotted line, it's able to still meet the kind of performance that you're looking for. The second thing that I'd like to go towards, that clock is really not working today. Okay, is state constraints. And again, Melanie talked about this and others as well yesterday. So you want to make sure also, in addition to making sure that your control input stays limited, that your state also stays within a desirable bound, and it has obvious connotations of safety. So how do you make sure that you are after your performance goal, and at the same time, you don't wander into unsafe territory? So one of the things that we were able to do is to stitch together the adaptive principles that I walked you through with the control barrier functions. And so this safety filter is different from the one that Melanie talked about, but I'm sure there are interesting intersections that we can explore. So what we do here is not only accommodate the fact that you've got uncertainties, and that basically requires you to adjust your control gains. You basically shape your command signal in a way so that this filter accommodates the constraints that you have to honor in terms of where the states should or shouldn't go. And we also have other kinds of interconnections between the adaptation part and the CBF part by designing some clever things into the reference model. So all of these things basically lead us to this result. So it's a first order example, very simple. We assumed again that there was a significant loss of effectiveness in the actuator. We specify the waypoints, and what you see is that from the various starting points, you want to hit the target without really hitting those obstacles. So if you really zoom in, it turns out that there is a little bit of a violation, and that's when these sort of clever things that we stitch together are really brought into the foray, and that is the notion of an error-based relaxation, and this basically allows you to not hit the obstacles and have your cake and eat it, so to speak. And so one of the things that we wanted to do was, hey, what if you really, really are very, very close to the obstacles? And the nice thing about the algorithm is that it figures out automatically on the fly the right path in order to make sure that your performance goals are met simultaneously, even while honoring safety. So again, all of this is it's the same kind of a game that we play. You don't know a priori that there is going to be this loss of effectiveness. The propeller blade can break at any point. You don't know that, and you cannot anticipate it, and that's where the adaptation really scores. So here's another example, and this is basically, well, that's really fast. That's not how it was playing on my screen. So what you see on the right side is really, for some reason the speed is really fast, is with adaptation. And this is a 6-DOF quad rotor with a nonlinear model. And what you see on the left side is where you don't have adaptation, and the pink path is what you really want to follow. And you can see in the picture on the right really does the job. Let me see how this one plays. So it's the same thing here, but using a photorealistic environment. So let me see, on the left side is you don't have the adaptation, and it's not able to figure out that it's got a compromised set of actuators, whereas on the right one, and those of you who know LIDS, you know that this is a status center at MIT, and this one actually figures out how to navigate the two pillars. And so here's again a nice demonstration that you can actually combine these two things. So these are not the only examples. There are any number of flight platforms that actually have been implemented over the years with flight tests that show that you can indeed have a successful flight control application in all of these things with improved performance and reliability. So now, what does all of this mean in terms of learning? So the question is, what is it that you learn in the context of doing all of these different things? Because we're really after performance in all of these examples. And so in order to learn, in this particular case, the learning is focused on parameters. What exactly went wrong? What's the kind of parametric uncertainty, the loss of effectiveness that you had? Is it possible for us to figure it out? And so that means that not only are you interested in your loss function going to 0, which is the E squared, something like an E squared, but the parameter error going to 0. And so question is, how do you do that? And obviously, the question is also, why do you need that? Because if you learn the parameters, what really gives you is a robustness guarantee. So, because even for a small change in the parameters, it's easy to see any number of examples where the corresponding change in the state space is significantly larger. So you do want to learn the parameters precisely. And the notion of persistent excitation is the one that really sort of gets you there, which basically says if you have n unknown parameters embedded in n equations, then you basically need to have n independent observations. So it's really a way of figuring that out. Either you can think of it as uniform observability, linear independence, a covariance matrix being non-singular, but all of these things basically give you the handle on the problem as to how to identify parameters. But then the nice thing about it is this is a necessary condition, which says that if you don't have it, you cannot identify the parameters. So you kind of rely on having excitation in your data, which is what people refer to as exploration, but a question is whether or not you can afford to have that when you're trying to do something in real time. And its excitation is not something that is easy to impose, for instance, if you're flying the aircraft, because not only the excitation means that you really have to have every direction of the in every eigenvector, you have to probe the system, and that might mean that you're exciting different kinds of roll and yaw and pitch inputs, which is not something that you want to subject the passengers to. So, but what it tells me is that if you are within a certain subspace, then it's going to not give you persistent excitation, whereas if you are able to probe all different directions, you can generate a full rank matrix, and that's something that is useful. However, in many problems, like I said before, you can't really guarantee persistent excitation. So now the question is, what happens with imperfect learning? And you don't want the imperfect learning to compromise your performance. So here's another example. If I have a high-performance aircraft, and it's in this particular case, it's a blended wing body, and it's open-loop unstable, and the short-period dynamics actually could wander into the right half of the complex plane. So if there is an uncertainty, so let's say that if there is no uncertainty, what you're seeing on the right side is the performance space, and the left side is the parameter space, and so the angle of attack basically has a certain kind of profile. But when there is an uncertainty, you can equivalently map it to a variation in the parameter from the theta, ideal value to something different, which you didn't know because you don't know the kind of modeling errors the system was subjected to. So if that happens, and if you don't really adapt in some way, you can actually have a huge impact. Remember what I told you about small variations in the parameter space can lead to a very large variation in the state, and here is one example. So what do you really want? You want to be able to wander back to theta star, which is the learning, but what if you can't? At least is there a compromise? Can I get something similar to the desired profile in the angle of attack space by figuring out if there is indeed some sort of a stable subspace and you wander into the stable subspace, even if you don't learn the parameters. So the goal here is really to make sure that even when you have imperfect learning, you have safe performance. In fact, this notion has been looked at quite a bit in the adaptive literature, which talks about this bursting phenomenon. And so the idea here is that, so let me just sort of walk you through this in here. So you're introducing a command signal, and let's assume that this 20 is like, 20 years or 20 centuries. You think that you've done your job because over that time frame, your loss function has gone to 0. But then there is a new data that happens, it comes much, much, much later. And when you do, because your learning error hasn't gone to 0, you basically relearn. And every time you relearn, your performance basically goes out of kilter. I mean, you need to, if you want to eat good food all the time, once in a while you have to go to a bad restaurant. That's sort of inevitable. Learning is part of really having locally bad performance, and that's what you're seeing in here. Whereas, if you are able to have a way of, and that's the imperfect learning and bursting, whereas if you have the right kind of exploration beforehand, the beauty of it is that it doesn't matter after, because your learning error has gone to 0, and your performance error has too, but then even if your data keeps changing, you don't bat an eyelid because you continue to really have a 0 loss function, which is fantastic. Right? So this is the difference between imperfect learning and learning. And so we really need to watch out for the fact that this bursting phenomenon doesn't occur just because your loss function has gone to zero, because especially when this problem is embedded in a complex dynamic system. So this is the point in here. This has been said a lot, so now let me switch gears and say, okay, now that I've told you all these wonderful things that adaptive control can do, how can we do, what's missing? What can we do better? What are the lessons that we can learn from the RL world, and see if there is a way in which you can even improve the scope of the problem that you're trying to deal with further. And we are after those kinds of tools. And again, thanks for setting the stage, Melanie, in terms of what we're trying to do here in terms of problem statement. So you have an unknown nonlinear function, and I didn't really say anything about optimality so far. So in everything that we talked about, there is a performance error. Yes, there is a loss function, but that may or may not completely relate to optimizing a cost, right? So if indeed that's what you're after, then what you want to do is to be able to figure out the control input, the policy, so that cost function is indeed minimized. And so the tool that we've seen again and is extremely popular is a neural network, and the idea, fundamental principle that the foundation on which it sits is the universal approximation theorem that says that your neural network will approximate whatever is that nonlinearity that you're trying to get your hands on, and you do that by basically estimating the weights in a deep learning architecture. And there, again, comes the similarity between the kinds of things that we've been doing in adaptive control, which is that there is some sort of a gradient descent function or modified gradient descent functions that tells you how to do this. So, and when you don't have uncertainties, which is really what we're trying to figure out, then all of these tools that you use needs to stitch together an approximation, and that approximation is through the path of neural networks, which gives you a way of doing the policy evaluation and the policy improvement. But then there are some things that you can say when you have a linear network, and things become a little hairy when you go into a nonlinear network. So this problem is being looked at and still has a long way to go in terms of having a nonlinear dynamic system really controlled using a neural network-based approach. So here is one, and here is a result from our group many, many years ago that says, okay, here is a problem that you're trying to have. Let's say that it is controllable, so a gamma of x comma t exists, but you're trying to figure out how you can approximate that using a neural network, and you guarantee that you can come up with a way of adjusting the weights so that the closed loop system is stable. So this is a Lyapunov-centric approach where we said, hey, let's assume that there is indeed a quadratic positive definite function, and somehow we're going to try and make that into a Lyapunov function, and we're going to basically train the weights. And our desired target is this nice negative definite quantity, and so then it gives you the kind of a loss function, and you adjust the weights, and the theorem that we came up with said that this is indeed something you can figure out how to train the network. And here's an example of a complex nonlinear problem where we were able to show what exactly the neural network brings into the picture and is able to give you stability. So another nice result that is in the literature is again from Andrea Krause's group, which then says that if you've got these kinds of uncertainties, then there is an optimal policy that you can design, and the problem gets complex because you're now trying to figure out what exactly is the interplay between the cost function that you pick and the Lyapunov-like story, which guarantees stability. And that basically is exactly what they do, where the policy is making sure that you always are able to stay within a level set determined by the Lyapunov function. So this interplay between picking an appropriate cost function and picking an appropriate Lyapunov function candidate is something that really has to be figured out, and is something that I think many groups are trying to see how to do that. So, and again, this is the theorem, and the only takeaway message I would like to convey here is that there are analytical guarantees that tells you how to use these safe model-based RL. So now, let's see if we can combine these two tools and take it one step further. And so, how am I doing with time? Okay, great. Okay, awesome, thank you. So this first example that I'd like to walk you through is one where you're using an RL for basically a reference system and the adaptive controller for the real-time adjustment because you've got your uncertainties that are occurring in real time online, which you didn't anticipate when you trained the neural network for the nominal system. So the point here is that you have a nominal system in here, and the nominal system basically is the one that you're going to use in order to set up the policy. And this whole thing has been trained using an RL. So as opposed to an RL-based policy where you're actually using the target model itself for the policy, we're going to take a different tack. And the different tack is that there's an outer loop, which basically has the RL system, but the inner loop is the one that has the adaptive controller. So that's what we're calling as the CRL. So the outer loop is this design in here, where this policy pi is based on the nominal design, whereas instead of using the distributional shift and assuming that the new things that you're saying stays within the distribution, what we are doing is basically to augment it using adaptation. And the adaptation, again, uses a very carefully designed performance error, et cetera, everything that I walked you through before. And because of you doing it in the right way, we can show that it's stable, and we can show that the performance error goes to 0. So what's the benefit of something? Well, here are some of the details. The main, again, point that I want you to get from this slide is that you have to have prior information about the structure. And the prior information about the structure basically is in the form of a regressor, because it says that the regressor is the one that is talking to the control input through these parameters, and that gives you a path for adjusting the parameters. And the regressor here contains nonlinear basis functions of the dynamics. It's got all of the information that you've learned using setting up your RL system. It's got the reference tracking error. All of those things basically goes into designing the regressor. And so the challenge here is, in a very complex unstructured system, how do you find the regressor? And that is, again, a problem that open problem that we're trying to chip away at. So here is the benefit of using something like this combined approach. So the example here is very similar to the quadrotor that I mentioned before, except we're making it a little bit harder, that it has to land on this moving platform. And not only that, even while it's doing that, it has to have a certain kind of performance. Obviously, it can't crash to the ground. It can't have too many of the variations in the XY plane. It can't wobble too much, either in the pitch or in the roll. And of course, the side slip velocity and et cetera all have to be within a certain limit. And it has to do all of this task within a certain time. So you can see that we're upping the ante in terms of what we mean by performance. And the performance is very unstructured. We are trying to really pose a problem where we really don't have a nice quadratic cost function. It's very hard to figure out what exactly is the terminal cost versus the finite horizon costs. And so all of those things make it a bit more challenging, but certainly I'm sure there are ideas from MPC that we can introduce in order to make the solution even better. So what this does, and again, what we considered here is, again, a 50% loss, and success rate is if any of those criteria are not met. And so in this particular case, actually, if you don't have the inner loop adaptation, the system actually crashes because we have a significant kind of loss of effect. The picture that I'm showing you is 50, but the numbers in the table show you for other kinds of loss of effectiveness all the way up to 75%. And whereas the inner loop adjustment of the control gains basically provides you with an additional degree of freedom and is able to cope with this particular kind of uncertainty that might occur. And the reason why it's able to basically do it is because we're using data that really is not something that has been pre-trained for. So if you use only the RL approach, if you look at the velocity, I'm not sure where my pointer is pointing to, but if you look at the direction in Z, you can see that there is a significant departure between what you think it is, which is the red curve, versus what it actually is, which is the blue curve. And therefore, anything that you design predicated on the red curve, which is your reference system, is no longer going to be sufficient, and that's the reason why And you can see that also showing up in the z dot direction, which is where the big red circle is. And because you're able to anticipate what exactly is the vertical velocity with the adaptive control augmentation, we are able to avoid the crash. The second example that I'd like to walk you through is a problem that actually was looked at. It's funny how, there's a sort of a Rip Van Winkle effect in here, things that happened 20 years ago, and it's true that many of these problems were looked at in the 80s, and a number of papers were written, and it basically somehow caught the attention of people working in the ML area, and that is this adaptive LQR problem. So what exactly is the connection to this example that I just said? ACRL basically allows you to learn a nominally optimal controller, but then it uses the adaptive control online to stabilize. So at the end of the day, when I tell you, oh, hey, it didn't crash, and I'm able to actually land, I am providing you with a stability-based solution, but it's not necessarily optimal. So is there a way in which we adapt, we learn, and then we optimize? And so can we take that through this step with minimal baggage? So we have to do it in that particular order, because if you predicate your design on learning, then you have this persistent excitation baggage, which you may or may not have. And so what we're trying to do in here is basically have a different approach. And again, the problem is in the context of this very simple linear time invariant dynamics and a quadratic cost function. So let me walk you through what we're trying to say in here. So you have the plant, which is a linear dynamics, and of course it's excited by noise. It's sort of very similar to the problem statement that Sarah had yesterday. And you have a controller, and it's based on the LQR design. You have a quadratic cost, and you introduce a certain amount of excitation in order to have the covariance matrix become non-singular. So what do you do? You collect the data from the input and the output, and then you come up with a parameter estimate. And it's basically, you collect this covariance matrix, and that's your Phi transposed, and you look at this metric V sub t, but you have to collect the data for a while, because you need to have full rank. And while you're collecting that data, remember this is an actual physical system, you have a control input. So whatever you have as an initial controller needs to be stabilizing. And if it's not, then you're going to be in trouble. And you've seen many examples so far. A quadrotor is really like an inverted pendulum. Even the propulsion system is, for instance, an unstable system. Hypersonic aircraft have short period modes that are unstable. There are many, many, many physical examples that do have instability, and therefore you do need to get your control gain right in the beginning. So what this means in here, the initial controller must be stabilizing for you to have data that is well conditioned. Okay. So then we need excitation, right? We need that covariance matrix to be non-singular in order to learn the parameters and stabilize. So these are the properties. So stability relies on excitation. Initial controller must be stabilizing. And there are many variations, and I'm combining many of the recent results in this one box. And sometimes if you want to be very exhaustive, then you need to have a very elaborate search. But if you are able to have parameters that are nearby, that are optimistic, then that basically relieves the optimization burden. So you can do all of these things. So, but is there a way in which we can come up with an algorithm that doesn't require any of these things? And I think we have a nice result that allows you to directly leverage adaptive control. And so the idea here is that you take a different approach where the direct adaptive control basically comes up with the adjustment gain without relying on the parameter estimation. And you basically use a recursively squares-based adaptive law to come up with a control gain, and that's the one that goes into the direct adaptive box. And using this information, you basically calculate a new reference model. And the reference model basically has a lot of thinking that goes into it. We think that that's the target. That's how we want our closed-loop system to behave. But if you have a compromised system, your closed-loop system cannot behave in the same way a pristine quadrotor whose propeller blades are not broken to behave. So the acknowledgement, the awareness as to what exactly went wrong, which is really what we're putting in the learning basket, is something that has to be looked at carefully. And that's what we're doing when we calculate the new reference model. So when you calculate this new reference model and you repeat the whole process, you can basically have the adaptation in place without requiring a stabilizing gain, learn the new parameters, which then goes into a new reference model, which then gives you a way of readjusting the control gains. And that basically allows you to bypass some of the restrictions that dependence on persistent excitation. So we use this approach, and I'm going to show you the results of two different dynamic systems. One is academic, where the Laplacian dynamics is marginally stable, and the initial feedback gain is destabilizing. And therefore in contrast to some of those methods, what we are able to do in terms of when we are basically using regret as a metric, so what we have is more optimal, and the state magnitude stays much smaller compared to some of the other methods. And I go back to my 6-DOF quadrotor example. Again, we introduced a front rotor that has 50% loss of effectiveness. And here too, we are looking at the regret, which gives you, again, more optimality, and the pitch angle stays smaller. So that's basically what I wanted to walk you through. Adaptive control basically takes an approach that we based on structured information about the model, but while acknowledging that parameters can be uncertain, you can design a real-time control algorithm which tells you how to structure the control input based on parametric estimates that you continuously adapt. And you do it in real time without requiring training. And there is a way to learn those unknown parameters, but that is predicated on persistent excitation. And there are ways in which you don't have to depend on that and have this imperfect learning, yet guaranteed performance. And I think we can expand the scope of what adaptive control can do by moving towards optimality. So now that we know how to adapt and we know how to learn, can we then really figure out how to be optimal and really have all of these sort of timescales over which we do, even though they might come in that order, happen over a much, much shorter interval. That, I think, is what we are going through, and we are leveraging some of the existing results that come with analytical guarantees and reinforcement learning, and I just walked you through a couple of examples. So overall, what we're trying to do in here is basically to have RL approaches and other safety-based approaches as well, and we are able to integrate some of those things together with adaptation and learning. And so in some cases, we really need to use this order, that you adapt first, and the guarantees with imperfect learning are essential, and learning comes with hindsight. And so as we move towards fully autonomous systems, some of these kinds of tools I think are important, and in some cases, control for learning, I think, needs to be addressed in addition to learning for control. So, thank you.